Physics class 12. Today we begin chapter 6, Electromagnetic Induction. What do we mean by electromagnetic induction? The phenomenon in which electric current is generated by varying magnetic field is called electromagnetic induction. There are some experiments done by two scientists. One is Michael Faraday in England and Joseph Henry in USA. They conducted the experiments separately, but they did during the same time, that is 1830. So the credit of these experiments goes to both of them. Experiment 6.1. In this experiment, what they did is they took a coil connected with a galvanometer. Galvanometer shows the presence of the current in the coil. And they took a bar magnet and brought closer to this. When they brought closer to this, they found the deflection in the coil. Deflection on the galvanometer, which shows the presence of current in the coil. Again, they took this away. Okay, so when they took this away, they again found the deflection in the galvanometer, which shows the presence of current. But this time when they took away, the direction was opposite to when they brought closer. Now they kept the magnet stationary and started moving the coil. So when they took coil away, they found the deflection in the galvanometer in one direction. When they brought closer, they found deflection in the opposite to the first one. So what, and then they keep the both together, kept stationary and moved together. Okay, so when they moved together also there was no deflection. So what they concluded is the relative motion between the magnet and coil generates electric current in a coil. Experiment number 2. In this, they replaced the magnet by another coil, and this coil had got battery connected. Again, the first coil that was called C1 and the second coil C2, this is kept stationary, and this is brought closer. When they brought closer, they found that there is a deflection in the galvanometer, which shows the presence of current in the coil in one direction. Then took away, they found another the deflection in opposite direction, so again there was a current. Kept this stationary and started moving this. When they moved this, again they found there is a deflection, brought closer in the opposite direction, they found the deflection. So they concluded that the relative motion between coil that generates electric current in the coil. Experiment number 3. In this, what they did is the second coil was connected with a key. A key was kept here. So now what they did, when the key was closed, okay, so you know that when the key is closed, there will be some current starting with a 0. It will not reach highest, but it will start from 0 to some steady current I. Okay, suppose steady current is I, so it will start from 0 to I. So during that time, there is fraction of time it will take. They show there was a deflection in the galvanometer. Again, when they open the key, that means the current was flowing steady current I, but it will now become 0. So from I to 0, that is also takes fraction of time. They found there was a deflection in the galvanometer in opposite sense. So they said that, and this time they are not moving both the coil or neither single coil. They kept both the coils stationary. Only the key was open and closed. So they found that it is not relative motion, but it is the change in the magnetic flux which gives the current in the coil. Okay, and how, let us see in this figure, first figure, how the flux is changed. So suppose I bring the coil magnet closer. So when I bring the magnet closer, it will have field lines. Okay, so when you bring the closer, the field line will increase. That means there will be change in the flux here. When I take away also, field line will become lesser, so that means there will be again change in the flux, and so there is a current in this coil. So this is what they experiment. They did 3, but there is so many, but conclusion is given from these 3. Then let us define magnetic flux, which we have defined in the last chapter also. Magnetic flux, it is denoted by phi b. Magnetic flux through a plane of area capital A placed in a uniform magnetic field B is phi b is equal to B dot A. B is a magnetic field, A is the area vector, and if I remove the dot product, I can write BA cos theta. Theta is the angle between B and A. Okay, and the unit of this is Weber. WB is the symbol used, or Tesla into meter square. Now suppose I have got the curved surface area and uniform magnetic field. Okay, something like this. Okay, in this figure you can see this is the curved, and it is magnetic field is not uniform. Okay, all the direction you can see. So what you have to do is you have to divide. Suppose this is my surface. Okay, so you divide small part, okay, into small area called dA, dA1, dA2 and dAn, and you calculate flux through each part, okay, through each part, and then total it and you get the total flux. Okay, so we can say like this: phi b is equal to b1 dot da1 plus b2 dot da2 plus up to plus sum all, so sigma all bi dot di. Summation can be written as integral b dot da, and magnetic flux is a scalar quantity. Next, after these experiments, as I said, they did not do only these three, they did many experiments and they come to a conclusion. They gave a law of induction, and it is known as Faraday's law of induction. So let us see the statement. The magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. So induced EMF E equal to change in the flux with respect to time, that is d phi by dt, and it is negative because direction, it is because of the direction. Suppose I have got n turns in the coil, then you multiply by capital N. Then the magnetic flux changes by varying B, A and theta. Why like that? Because we have already seen that the phi B is equal to BA cos theta. So phi depends on B, phi depends on A, and theta between A and B. Okay. Therefore, if you want to change in the magnetic flux, it will either you change B, A or theta. So we'll keep this much. Next we will see Lenz's law and conservation of energy. Thank you very much.